Iceman. Let's see now. Voltage, in an inductive circuit, voltage leads the current. In a capacitive circuit, current leads the voltage.
E leads I, and yeah, voltage leads the current. And
Eli the Iceman? Oh, ELI. So in an inductive circuit, one where it's reactively inductive, the voltage leads the current. In a capacitive circuit, reactively capacitive circuit, the I leads the E, so the current leads the voltage.
Basically, the capacitor has to have current into it before the voltage can build up across it.
I didn't want to show you all the calculus for that, but basically that's it in a nutshell, the calculus. You need to have the voltage in, you need to get voltage into an inductor before you can have any current flowing. If you want to block RF, what you do is you put an inductor, a high Henry, a very strongly inductive inductor, and it's called a choke. It will block the AC part of your circuit, but it will allow DC, so you can bias your transistor, you can bias your tubes, so you can keep it at a nice steady voltage, but it doesn't like change. Capacitors love change, but they won't pass DC at all. So if you want to block DC, you put a capacitor in the circuit.
I look at it from the point of the magnetic lines in an inductor. Once you get the current built up from the DC, the magnetic lines are around it. If the AC tries to change, the magnetic lines start to collapse and keep the current moving the same direction it was going before.
And just the opposite for a capacitor. Once you charge a capacitor, it will hold the current. It will hold voltage. So, say you're making a power supply. So the first thing, you come into a transformer and you transform it to a voltage you want. So 125 volts to 15 volts, let's say. Then you change it into DC, but the DC still has ripples in it. Well, now you put a capacitor in there to allow you to use a little bit of voltage in all the gaps. So it keeps the voltage at a steady state. It actually allows you to use some of the voltage in the capacitor over time. An inductor does just the opposite, but it allows you to use that. This is where resonance and a tank coil come in. This is a few slides down the road.
The inductor tries to keep the current constant. The capacitor tries to keep the voltage constant.
We're getting there. Reactance is essentially inertia against the motion of electrons. And that's what we've been trying to say with too many words. It is present anywhere electric or magnetic fields are developed in proportion to applied voltage or current, but most notably in capacitors and inductors. Any bit of wire on a circuit board has inductance and capacitance and resistance. Everything's there. It's only more present at certain frequencies than it is in others. If you want to make a 40-meter transceiver, a lot of these things aren't very noticeable. If you want to make a 1 gigahertz receiver, you have to be very, very careful even how you curve the edges of your traces, how thick your trace is, and what the surface on the bottom of the trace looks like. Skin effect will drive you crazy because at a very high frequency, the actual current only flows in the outside of the conductor.
And the stray capacity is not very stray anymore.
In UHF circuits, you can actually have the current go off of the wire, continue on in a straight line, and jump to the next wire that's in a row. That's why you need to make sure you curve properly. If you look at an old TV tuner from the 50s and take apart the tuner, you will see the wires are curved just so to make them work. Very interesting stuff. When alternating current goes through a pure reactance, a voltage drop is produced that is 90 degrees out of phase. This is the Eli the Iceman did. Reactance is mathematically represented by the letter X and is measured in ohms. Impedance is a comprehensive expression of any and all forms of opposition to electron flow, including both resistance and reactance. It is present in all circuits and in all components. When alternating current goes through an impedance, a voltage drop is produced that is somewhere between 0 degrees and 90 degrees out of phase. It is not perfectly at 90 degrees like a pure inductor or a pure capacitor are. Impedance is mathematically represented by the letter Z and is measured in ohms. But this is in a complex form, so you're going to have J in there. Electrical engineers used I long before they came up with complex numbers, so when you see the square root of -1 in electrical work, it's always going to be J, not I. I is current. If you see it in a mathematics book or a physics book, they're going to use I for the square root of -1. It's one of those things you just got to know. And here are the two little things you need to know for reactance. You will be doing some equations later with these. They're all worked out, so you don't need your calculators. You're just going to follow along step by step. But this is capacitive reactance and inductive reactance. F is frequency in hertz, C is capacitance in farads, and L is inductance in henries. I will have to tell you, henries and farads are huge. It's easy to get 1 to 100 ohms, but to get 1 farad, a 1 farad capacitor used to be very, very large, if you could even find one. Now they're getting smaller, but still, 1 farad is a very big unit. And if you see a 1 farad capacitor that's charged, do not touch it. Because even if it has been discharged in the last minute or so, it's picking up stray electricity, and it might just kill you. Impedance is the AC form of resistance. I mentioned that before. So here's where Z, R, and X all come together. And if you'll notice, capacitive reactance is negative, and inductive reactance, I didn't really know if I wanted to put a capital L there or not. That is an L, it's not X on, that's an L, sorry.
I'd usually sub L. In most of the places I see it is X sub C.
Normally it is
X
sub L, but if you wanted to go through all the time of making the sub L and doing all that work, it is possible. And here's the square root of -1. These slides will go up onto the website. I will try to add my notes, and these notes will try to get on there too, and everything will be up there in one piece. Don't fall asleep, Frank. Now here's the whole complex plane. If you'll notice, the inductive reactance axis is up or positive, like it was back here. Inductance is positive, and capacitance is negative. That's what happens down here. In this circuit, you're putting, in the top circuit, you have resistance in parallel with an inductance. And here's the vector notation of, here's the fully inductive part of the reactance, and here's the resistance part. When you add the vectors together, this is what you wind up with, and it looks like it's, 60 degrees. So you're going to have whatever distance that is at 60 degrees. Wow, that's bright. Same down here with the capacitance. And if you worked your way through the extra class license manual, you went through a lot of these.
Good, you're not getting a negative R yet anyway, huh?
Whew. No. A negative R would be a tunnel diode.
Yeah, oscillators.
And here's another example, and we're putting capacitance and inductance. But in this case, inductance goes straight up, capacitance goes straight down, because we're considering these pure, even though the real world is not pure. There's going to be some resistance in there, so they're not going to be absolutely plus and minus 90 degrees, but since this is going to be math, we're going to do it absolutely perfectly mathematically. If you wanted to, what you do is you put this on an oscilloscope and you start reading what's actually going to happen, or you look at it with a grid dip oscillator and you go, this is what's really here. But in this case, we're just going to do pure math. This is just a simple example to show you why some of those things work. On the right, we basically have a tank coil.